Right now, there's a mysterious visitor speeding through our solar system. It's called 3I/Atlas, and get this, it comes from a completely different star system. As it gets closer to our sun, it's literally morphing right in front of our eyes, and it's leaving scientists with this trail of absolutely baffling clues. Okay, let's dive into this cosmic detective story.
And right from the get-go, the research is hinting at something huge. This isn't just another comet. You know, when scientists use phrases like a previously unobserved class, that's code for we found something brand new. We've stumbled upon a new kind of object, a visitor carrying secrets about how other star systems are built. The rulebook? Yeah, it might need a complete rewrite.
So, our investigation begins with an interstellar enigma, a puzzle that traveled light years to land, well, right on our cosmic doorstep.
This is the big question, right? Is it a comet, an asteroid, or is it something else entirely? To figure that out, we have to look at the evidence. And let me tell you, right away, the first observations were deeply, deeply strange. Okay, so first off, it's Coma. That's the fuzzy cloud of gas and dust boiling off its surface is already half the size of our sun, and it's still growing. Its surface is this dark reddish color, which is pretty typical for objects from the cold, distant edges of star systems. But early on, it had a tail that pointed towards the sun. Think about that. No other comet has ever been seen doing that. The crucial point here is, it's not behaving like anything we've seen before.
All right, our first major piece of evidence comes from how this object plays with light. And this is where the mystery really starts to deepen.
So scientists used a technique called polarimetry to study the light reflecting off Atlas's Coma. And what they saw was incredible. It shows that the Coma isn't just some simple, uniform cloud. Nope. Instead, it has these complex, evolving structures inside of it, patterns that have grown and changed over time.
So what are we actually looking at here? I mean, what do these patterns mean? Well, they're vital clues about the Coma's physical properties. And to decode them, we need a quick crash course on a fundamental property of light. In simple terms, a wave of light has an electric field that vibrates. Polarization is just the direction of that vibration. You can kind of think of it as the orientation of the light wave as it's traveling through space.
The easiest way to picture it is with polarized sunglasses. Sunlight is normally unpolarized, right? The light waves are vibrating in every direction imaginable. But the filter in your sunglasses, it blocks all the waves except for the ones vibrating in one specific direction. What gets through to your eyes is polarized light. Simple as that. Okay, so bringing this back to Atlas, those patterns of positive and negative polarization, they aren't just random noise. They show us an organized structure, almost like a double layer. Scientists look at this and see a clear signature of a complex plasma environment. We're not talking about simple gas and dust anymore. This is a dynamic, electrically charged system, governed by physics we don't typically see in comets. And as if that wasn't strange enough, our interstellar visitor recently threw us another major curveball. A second, very visible clue has just emerged. That's right. Astronomers capturing recent pictures of 3I/Atlas were greeted with this vibrant green hue. Now, you might be thinking, so what? Comets glow green all the time. And you'd be right. But that's precisely what makes this so incredibly weird. See, usually a comet's green glow comes from a molecule called diatomic carbon, or C2, getting zapped by sunlight. But here's the catch. Observations of Atlas show it's actually depleted in C2. It doesn't seem to have enough of the key ingredient to glow green. This means its glow must be powered by some other process, something scientists are literally calling unfamiliar chemistry. So we've got a strange structure and a mysterious glow. Let's now compare our suspect to the usual lineup of celestial objects and see where it fits. Or, as it turns out, where it really doesn't. You know, one of the best ways to identify an object is by its polarization fingerprint. Specifically, scientists look at the angle where the light reflecting off it flips from negative to positive polarization. This inversion angle is a key diagnostic tool, like a cosmic fingerprint. And this table just lays the problem bare. Typical comets, and even the other interstellar comet we've seen, Borisov, they all have an inversion angle around 21 degrees. But just look at 3I/Atlas. Its fingerprint is completely different. Its curved shape is actually more similar to trans-Neptunian objects, or TNOs, those icy bodies like Pluto that orbit way out in the cold reaches of our own solar system. Let's just focus on that number for a second. 17 degrees. Now, that might not sound like a huge difference from 21 degrees, but in polarimetry, it's a massive deviation. It is the lowest inversion angle ever recorded for any comet-like object. It firmly puts this thing in a class of its own. And if that isn't enough to set it apart, there's its speed. At its closest approach to the sun, it'll be traveling at 68 kilometers per second. That's over 150,000 miles per hour. That is an absolute speed record for any object we have ever observed passing through our solar system. Just incredible.
So what's next for this record-breaking, mysterious object? Well, the investigation is far from over. In fact, some of the most exciting moments are still just ahead of us.
And this story is still unfolding. On October 3rd, it makes its closest approach to Mars, which gives a probe orbiting the red planet a chance to snap a high-resolution photo. Then, on October 29th, it hits Perihelion, its closest and hottest encounter with the sun. And way out in 2026, it's going to have a close brush with Jupiter. Each one of these moments is a brand new opportunity to gather more clues. So, let's summarize the case file. We have a complex, structured plasma coma, we have a mysterious green glow from unknown chemistry, and we have a polarization fingerprint that doesn't match anything in our entire catalog. The evidence is just mounting up. The inescapable conclusion is that 3I Atlas isn't just a weird comet, it truly represents something new to science. You know, the journey of 3I/ATLS is this stunning reminder that the universe is filled with objects and processes we haven't even imagined yet. It makes you wonder, doesn't it? What other interstellar messengers are out there right now, carrying secrets from distant stars, just waiting for us to find them?
Welcome to the debate. Today we are tackling, one of the most intellectually compelling puzzles presented by an interstellar visitor in quite some time. 3 Atlas, as this enigmatic object charges toward its perihelion near the end of October, the accumulated observational data, particularly its speed, its chemical signatures, and frankly, its bizarre polarization profile, is making typical classification, let's just say, utterly impossible.
Indeed. And because 3I Atlas originates from a completely different stellar nursery, a different celestial neighborhood altogether, it's perhaps not surprising that it behaves differently. But the core question dividing experts right now is really about classification. Does the extreme nature of 3I Atlas mandate its immediate classification as a, quote, previously unobserved class of small planetary bodies? Or are we seeing behaviors that, while definitely unprecedented, still fall within the, let's say, extreme boundaries of known populations, such as comets or maybe trans-Neptunian objects?
Right. And I'm arguing that the sheer convergence of these extreme, seemingly uncorrelated properties, from its kinematics, its sheer speed, to its light scattering profile, it forces us, really, to designate 3I Atlas as a distinct class. Our current solar system frameworks, which were, developed for gravitationally bound objects, they're simply inadequate to capture the physical reality of this interstellar relic. It is fundamentally new.
Okay. I come at it from a slightly different perspective, emphasizing caution. While 3 Atlas is undeniably extraordinary, key data points do show some striking similarities to existing solar system objects, specifically trans-Neptunian objects, or TNOs. Furthermore, the object is exhibiting core cometary activities. So I maintain that creating a whole new physical class right now is premature, especially when the most fundamental characteristics of the object, namely its size and density, remain wildly uncertain.
Okay, let's delve immediately into the evidence that I think demands a new category, starting with what we know for certain about its trajectory. Its velocity is not just fast, it's record-breaking. It's currently moving around 60 kilometers per second, and at perihelion, that speed is predicted to hit 68 kilometers per second. Now, this is a velocity we have never observed in an active body traveling through our solar system. This interstellar velocity for me is the clearest indicator that its formation conditions were completely distinct from anything formed within the sun's gravitational sphere of influence, including the Oort cloud or the Kuiper belt. Kinematically, this object is a relic from somewhere else, and that fundamental difference must be reflected in its classification.
That's a powerful point regarding the sheer speed, I grant you that. But I would argue that velocity tells us about its history and its trajectory, not necessarily its compositional class, right? We have to look at how solar radiation interacts with it, and that brings us to the structure and the light scattering you mentioned. So while 3 Atlas is unusual, key pieces of data show striking similarities to existing solar system objects, making the creation of a new class, I think, premature. If we look at the polarization data, which measures how light is scattered off the disk grains, giving us clues about their size, texture, porosity, the extrapolated curve of 3 Atlas shows a pretty striking resemblance to trans-Neptunian objects, TNOs. These are those dark, icy bodies way out past Neptune's orbit. And this compositional alignment seems reinforced by its established dark reddish color, which is, well, a common characteristic of TNOs that have been exposed to high-energy radiation in the deep outer solar system or even interstellar space. So, while its behavior is extreme, its fundamental composition appears to align with a known population of dark, heavily irradiated, volatile-rich objects. That suggests it might just be ejecta from another system's TNO equivalent.
I see why you emphasize the dark reddish color as a compositional link, yeah. But the overall shape of the curve, especially an extrapolated one, is far less diagnostic, I would argue, than the specific anomalies we've actually measured. Let's focus on the geometry of the light scattering itself. When astronomers discuss polarization, we're looking at the phase angle. That's the angle between the sun, the object, and us, the observer. And the point where the scattered light flips from negative to positive polarization is called the inversion point. Now, for 3 Atlas, the inversion point is measured at a very low 17 degrees. This is significantly lower than the average comet, which typically inverts around 20 degrees. This difference isn't just some minor statistical variation. A lower inversion point implies a really radical difference in the dust properties. It strongly suggests the presence of highly porous, maybe fractal dust aggregates. Grains that are highly irregularly shaped and scatter light in a way that simply isn't seen in our local cometary populations, not even in the most unusual ones like Hale-Bopp. This specific deep negative polarization value, minus 2.7% at 7 degrees phase angle, it provides physical evidence of a fundamentally different surface and comma structure.
Okay. That's an interesting point about the specific value, though. I would frame the physical structure maybe differently. You emphasize the numerical anomaly of the 17-degree inversion, but are we perhaps confusing extreme conditions with fundamental uniqueness? The overall alignment of the polarization curve still suggests a link to the TNO population, meaning maybe the bulk material is similar, but the grains are perhaps just finer or more volatile, leading to that lower inversion point. Furthermore, let's discuss the highly complex structures you mentioned forming in the Coma, which you suggested resemble plasma double layers, these distinct rings of positive and negative polarization. You suggested this is evidence of unique, non-cometary physics. I challenge that assumption. We know that any active body that contains gas and dust and gets close enough to the sun will become ionized and form a complex dusty plasma. The formation of plasma double layers, where you get distinct regions of positive and negative charge separating, is a recognized electromagnetic phenomenon in extreme cometary environments. It simply means the scale of activity is massive. The Coma is already half the size of the sun, remember? But it likely fits within the recognized physics of complex dusty plasma formation. It's extreme, yes, but maybe not fundamentally new physics.
Well, if the physics of the Coma were simply scaled up, we should see corresponding chemical signatures that match known cometary activity. And this brings us to the chemical anomaly, specifically the green glow. Now, comets often glow green when they approach the sun because solar radiation excites diatomic carbon, C2. That green glow is, as you say, a familiar sight. However, based on spectroscopic data gathered earlier this summer, 3I Atlas was notably depleted in C2. Now that it is closer to the sun, it is glowing green. So if the C2 production hasn't suddenly and massively just turned on, which would be highly unusual given its previous depletion, this green glow strongly suggests unfamiliar chemistry. It means some highly volatile, perhaps exotic compound, one we haven't really categorized in our solar system's active bodies, is being excited by solar radiation. This feels like strong evidence of a unique interstellar composition that warrants its own classification framework. we could be looking at potential chemistry from a completely different star's formation disk.
I'm sorry, but I just don't quite buy that the green glow immediately proves unfamiliar chemistry. The observation of the green glow for me links it back powerfully to known categories. The article itself states that the green glow is a familiar sight for comets. Yes, okay, it might have been C2 depleted when it was far out, but the object is currently zooming through the asteroid belt and will pass extremely close to Mars. It is subject to extreme solar radiative influence, the like of which we haven't measured before for this specific object under these conditions. This rapid proximity to the sun might have rapidly increased the production of C2 from larger parent molecules hidden deeper within, or maybe triggered a known, albeit extreme photochemical process that simply requires a massive heat spike like this. A developing, quote, more of a normal tail confirms it is undergoing solar-driven activity exactly like a comet. We cannot prioritize a chemical uncertainty or anomaly over the exhibition of expected fundamental cometary activity near Perihelion. It looks like a comet, it's acting like a comet.
But I'm not convinced by that line of reasoning because you seem to be dismissing the kinematic evidence, the speed, which dictates its origin, in favor of focusing solely on the resulting activity driven by our sun. That high speed, that predicted 68 kilometers per second, is still the most compelling evidence that its formation conditions were completely distinct. Prioritizing the fact that it is behaving like a comet now, in terms of developing a tail, ignores the overwhelming evidence that it is traveling at a speed incompatible with any known gravitationally bound solar system population, TNOs included. If its material shares some properties with TNOs, fine. Maybe that suggests TNOs or their equivalents are sort of the baseline for interstellar objects ejected from other systems. But the speed proves this is a relic of a completely different stellar nursery, meaning its internal structure and chemistry simply cannot be governed by the norms of objects formed in our sun's Oort cloud or Kuiper belt. The abstract, calling it a previously unobserved class, reflects the necessity, I think, to account for this cumulatively unique physical and kinematic behavior. It's the whole package.
Okay, that is a crucial distinction you're making. The difference between kinematic history and physical classification. And while the speed absolutely guarantees an interstellar origin, I agree, classification must be based on the physical nature of the object itself, not just its trajectory through space. And this is where my major concern lies. We simply lack the basic physical metrics to define a new class with any confidence. Look, we have wildly disparate estimates for the size of its nucleus, ranging from a minuscule 0.2 kilometers up to maybe 50 kilometers in diameter. That is a huge range. This massive uncertainty means we cannot accurately calculate its mass or its density. How can we possibly define a new type of small planetary body when its fundamental size is basically unknown? We're actually in a pretty favorable position because a reconnaissance probe near Mars is expected to take a high-resolution photo around October 3rd. Until that high-resolution data allows us to refine the size estimates based on albedo and truly define the object's mass, classifying a whole new type based solely on speed and some highly nuanced polarization data feels premature. We need to know what we are classifying first.
I understand the constraint posed by the size uncertainty, I really do. But that constraint shouldn't paralyze classification when the behavioral data is so conclusive, so extreme. We are talking about extremes across the board. The fastest object ever measured through the system, producing the most bizarre polarization curve ever measured, and exhibiting a coma half the size of the sun already. If we wait for perfect data, we miss the opportunity to categorize a phenomenon that is happening right now under our observation. This object's unique combination of high speed and radical surface structure, for me, fundamentally separates it from known comets and TNOs, regardless of the exact nucleus size within that range.
But the physical uncertainty is the definition of the object. If the 0.2 kilometer estimate turns out to be correct, it's an extremely small, highly volatile object, which would align much better with being just an extreme, maybe unusually structured comet. If the 50 kilometer estimate is correct, well, then it's a truly large, planetesimal scale body, which requires an entirely different discussion about its physics and heat retention and internal structure. We're basically debating whether to create a new shelf in the astronomical library when we don't know if the book we're holding is a pamphlet or a massive volume of encyclopedias. We should prioritize defining its physical characteristics based on the upcoming imagery before we start redefining the whole classification system.
Okay, well, to summarize my position then, the confluence of unique characteristics, the record-breaking interstellar velocity that dictates its foreign origin, the extreme polarization curve suggesting unique dust morphology, and the green glow anomaly potentially suggesting unfamiliar chemistry, all demonstrate that 3.8 Atlas is fundamentally distinct. Its cumulative behavior operates outside the established physical constraints of known comets and TNOs, and I believe this justifies its proposed designation as a new class of object.
And to summarize my view, while I readily accept the object is unusual, perhaps spectacularly so, its compositional link suggested by the dark reddish color and its overall polarization resemblance to TNOs, coupled with the exhibition of recognizable cometary features, massive coma growth, tail formation as it nears the sun, suggest it may simply be an extreme, maybe record-breaking variant of existing interstellar travelers, perhaps originating from an exo-Oort cloud or exo-Kuiper belt. Caution is required until the critical physical data, particularly the nucleus size and resulting mass estimate, is obtained during its flyby near Mars and subsequent perihelion. Premature classification based on parameters that are still quite uncertain is, I think, risky.
Well, regardless of which classification ultimately prevails or how we refine it, 3 Atlas certainly continues to illustrate the complexity and the sheer variety of interstellar visitors that populate the galaxy. It's quite a messenger.
Absolutely. And it strongly reminds us that scientists must maintain open and flexible frameworks for classification as new data, particularly that high-resolution imagery from its close past, emerges in the coming weeks. It's going to be fascinating to see.